To ensure stability, 40 to 100 geopiers are strategically installed beneath the turbine site, reinforcing the soil. The process includes excavating a 10-foot deep foundation to anchor the turbine securely. The foundation spans a robust 100-foot wide area. Excavating the 100-foot wide area requires significant effort and time. Up to 96,000 pounds of reinforcing steel are embedded, while as many as 53 concrete trucks deliver material to ensure a robust and durable turbine foundation. Each turbine blade measures an impressive 173 feet in length and weighs approximately 27,000 pounds, showcasing advanced engineering. Transporting the turbine components to the site requires 8 truckloads due to their immense size and weight. Each truck carefully carries critical parts, including the tower segments, blades, and nacelle, ensuring safe delivery for assembly. Specialized vehicles handle the oversized loads efficiently. The nacelle, comparable in size to a school bus, is a powerhouse of the turbine, housing essential components like the generator, gearbox, and control systems. It weighs 181,000 pounds. Its robust design ensures durability and efficiency, enabling the turbine to convert wind energy into electricity seamlessly. The base tower stands 53 feet 11 inches tall, providing a sturdy foundation for the turbine's towering structure. The base tower weighs an impressive 97,459 pounds, ensuring stability and strength to support the turbine's massive upper components. The base tower is secured with 160 bolts for maximum stability. The mid-tower reaches a height of 84 feet 6 inches. The mid-tower weighs 115,587 pounds, adding significant structural support to the overall turbine. This hefty component is designed to withstand extreme weather conditions and mechanical stress while maintaining the stability of the entire structure. Its robust weight ensures the tower can securely hold the nacelle and rotor assembly, critical for the turbine's efficient operation. The rotor assembly is a crucial part of the turbine, responsible for converting wind energy into mechanical energy. With a diameter of 354 feet, the rotor includes the blades, hub, and other components. Assembling the rotor typically takes around 4 hours, requiring precise coordination and skilled labor to ensure each part is correctly attached and aligned for optimal performance. The top tower reaches an impressive height of 119 feet. The top tower section weighs 104,167 pounds, providing vital structural support for the turbine. This heavy component ensures the turbine can withstand harsh environmental conditions and mechanical stresses while supporting the nacelle and rotor assembly at significant heights. The nacelle weighs 181,000 pounds, housing critical turbine components efficiently. The average time to prepare and raise the nacelle to the tower top is significant, typically requiring hours of careful coordination. The process involves securing the nacelle, using cranes or other equipment, and ensuring stability during the lift to prevent damage or misalignment. The rotor has a massive diameter of 354 feet, allowing it to capture large amounts of wind energy efficiently. The final tower height, including the extended blades, reaches 442 feet. The GE Renewable Energy Plant in Pensacola, Florida, is a key player in the manufacturing of wind turbine components. Located near Escambia Bay, this facility spans nearly 800,000 square feet and is home to one of the largest onshore wind component manufacturers in GE's global portfolio. With its beautiful surroundings and impressive infrastructure, the Pensacola plant is a vital contributor to GE's mission to provide cost-effective clean wind energy components. The plant employs about 600 workers across 3 shifts, producing crucial turbine components, including machine heads, hubs, and drivetrains. It has transformed over the years, shifting from batch production to a highly efficient assembly line system. This change, initiated in 2016, has significantly increased production capacity, allowing the plant to assemble over 100 wind turbine components each week. The focus on continuous improvement and lean manufacturing ensures that GE Pensacola remains at the forefront of wind energy production. The installation of the first tower elements involves assembling the foundation and the initial sections of the tower. Large crane systems are used to lift and position the tower segments, which are securely bolted together. These segments are typically made of steel and designed to withstand high wind loads. This step provides the structural support for the nacelle, drivetrain, and blades. The nacelle lift involves using a large crane to carefully raise the nacelle, positioning it atop the tower for secure attachment. The drivetrain and hub connection involves aligning and securing the drivetrain to the hub, ensuring proper mechanical and electrical integration. The drivetrain and hub are fully integrated within the nacelle, and the nacelle roof is installed to protect internal components. This step ensures structural integrity, weather protection, and proper functioning of the turbine. Lowering drivetrain into nacelle. Single blade installation involves lifting each blade individually using specialized cranes. The blade is carefully positioned and attached to the hub using bolts and hydraulic systems. Precise alignment is essential to ensure optimal aerodynamic performance. After securing the blade, the process is repeated for the remaining blades. Proper installation ensures the turbine's efficient energy capture and stability during operation. Design and construction involve engineering, material selection, and component integration. Production of contact systems involves creating durable, conductive materials, ensuring optimal electrical conduction, minimizing wear, and maintaining reliability under high currents. Production of contact systems involves precise fabrication of durable, high-conductivity materials, ensuring efficient current flow and minimal heat generation during operation. Washing ensures removal of contaminants, preventing defects and ensuring reliability. Assembly in a cleanroom ensures contamination-free conditions, maintaining component integrity by preventing dust or particles from affecting sensitive parts. One-shot vacuum sealing braze creates airtight, durable seals for interrupters. Quality testing of the vacuum interrupter. Vacuum level check ensures proper vacuum quality for optimal arc quenching performance. Dielectric testing verifies the component's ability to withstand high voltages without electrical breakdown, ensuring safety and reliability under stress. Assembly of the circuit breaker involves integrating the interrupter, contacts, control mechanisms, and housing, ensuring proper alignment and functionality. Quality testing of the circuit breaker. Mechanical operating test ensures reliable movement and functionality under normal conditions. Dielectric testing ensures insulation can withstand high voltage without failure. Assembly of the circuit breaker involves integrating all components, including the vacuum interrupter, contact systems, mechanical and electrical controls, and protective housings, ensuring proper alignment, functionality, and safety for reliable operation. Routine testing ensures the circuit breaker operates correctly under standard conditions, verifying mechanical, electrical, and dielectric performance before deployment. Building a large electric generator involves a complex, multi-step process that integrates advanced technology and precision engineering. The process begins with the creation of key components, such as the stator and rotor, which are the heart of the generator. These components are produced in specialized manufacturing facilities that utilize state-of-the-art machinery and techniques. The first step is the construction of the stator, the part of the generator responsible for converting mechanical energy into electrical energy. The stator core is made from stacked layers of steel that induce voltage. The layers are carefully stacked and tensioned to create a robust structure capable of withstanding high levels of electrical stress. After this, the stator undergoes a process called impregnation, where it is filled with resin in a vacuum chamber to remove air pockets and ensure durability. Next, the rotor, which rotates inside the stator to generate electricity, is assembled. The rotor is carefully manufactured and shaped, with all parts tested for accuracy and quality. The rotor is then heated to fit the rotor cap, a crucial part that secures the rotor's functioning within the generator. Once the stator and rotor are completed, the assembly process begins. The wetting process is a key step, where the stator and rotor are brought together. This is a critical moment in generator construction, as it marks the joining of the two major components, which will then work together to produce electricity. Throughout the construction process, each part undergoes rigorous quality control, including tests for cleanliness, accuracy, and functionality. The generator is also subjected to extensive performance tests, including simulations of potential malfunction scenarios, to ensure that it will operate reliably and efficiently in real-world conditions. Turning is a machining process where a rotating workpiece is fed against a cutting tool to remove material. It is used to create cylindrical shapes, refine surfaces, and achieve precise dimensions. Assembly is a critical phase in the valve manufacturing process, where individual components are carefully put together to form the complete valve. This includes aligning and fitting parts such as the valve body, stem, butterfly disc, seals, and actuators. During assembly, precision is key to ensure that each component functions correctly and meets operational standards. The valve's internal parts are checked for proper movement, tight sealing, and alignment. Any necessary adjustments are made to guarantee smooth operation. After assembly, the valve undergoes further testing to verify its performance before proceeding to quality control and final inspection. Drilling of the disc and shaft is an essential process in valve manufacturing, where precise holes are created to allow for secure attachment and proper functionality. For the disc, drilling ensures that mounting holes for the shaft are perfectly aligned, allowing smooth rotation. The shaft itself is drilled to accommodate bearings or seals that reduce friction and ensure durability. The drilling process requires high precision to maintain tight tolerances, preventing issues such as misalignment or leakage, which could compromise valve performance. An integrated dismantling joint is a specialized component used in valve systems to facilitate maintenance and removal. It connects the valve to the pipeline, allowing for easy disassembly without the need for cutting or disturbing the pipeline. The joint typically includes flanges, bolts, and gaskets, ensuring a secure, leak-proof connection while enabling efficient access to the valve for repairs or replacement. Hydroelectric assembly refers to the integration of VAG's advanced safety valve systems designed for critical applications. These assemblies combine robust valve components with safety features to ensure reliable performance under high pressure and flow conditions. The VAG-HISIC system includes specialized sealing technology, precise control mechanisms, and safety-enhancing components, all assembled to provide secure and efficient operation in demanding environments, hydropower stations, and industrial plants. Drilling the actuator on the valve involves creating precise holes to securely mount the actuator, ensuring proper alignment and functionality. Testing of the valves involves several stages, including pressure tests to check for leaks and verify structural integrity, as well as functional tests to ensure proper operation, including opening, closing, and self-closing mechanisms. These tests ensure the valve meets safety and performance standards. The disassembly of old valves involves carefully removing the existing valves from the pipeline system without damaging surrounding components. This process includes loosening bolts, disconnecting the actuator, and safely detaching the valve from its mounting position. Once removed, the old valves are inspected for wear or damage. The installation of new valves, such as the VAG EKN H1200 butterfly valves, begins by ensuring proper alignment with the pipeline. The new valves are securely bolted into place, and the actuator is connected. After installation, the valves are tested for proper function, sealing, and safety before the system is recommissioned for operation. Rotor removal in large industrial generators is a highly complex and delicate process, requiring precision, specialized equipment, and careful coordination. In the case of a 32 megawatts, 127,000 pounds generator, the process involves the removal of a rotor weighing over 45,000 pounds, with a slim margin of error of just 3/4 in radial clearance. This task demands the highest level of technical expertise and the use of custom-engineered tools to ensure the rotor is removed safely and without damage. At Smith Services, the rotor removal begins with a custom 20-foot-long steel tube designed specifically for the job. The tube, with a 1-inch wall thickness and weighing approximately 3,300 pounds, acts as a guiding structure for the rotor. The tube ensures that the rotor moves smoothly and evenly while preventing any risk of misalignment that could lead to damage. Two 50-ton cranes are used to lift and float the rotor, providing the necessary lifting power to handle such a massive component. The removal process requires meticulous planning and precise execution. The 3/4 clearance in radial space means every inch counts, and even small miscalculations can lead to costly mistakes. The cranes must be operated in perfect sync, with the steel tube guiding the rotor along the exact path. Once the rotor is in position, it is carefully lowered onto a set of supports or wheels for transport to a designated repair or inspection area. The challenges of rotor removal are further compounded by the size and weight of the equipment. With the generator weighing 127,000 pounds, the task of safely removing such a large and heavy component involves managing significant physical forces. Unloading the truck required disassembly of the generator, including detaching protective covers and components. This was necessary to access the individual parts, the rotor and stator, for safe handling and repair. Removing the rotor from the stator involved carefully detaching the rotor's mounting points, ensuring precise alignment. The process required meticulous coordination to avoid damage, as both components are heavy and sensitive. Two cranes were strategically positioned to lift the heavy rotor from the stator, requiring precise coordination to ensure balance and prevent any shifting during the process. One crane was used to support the front of the rotor, while the second crane lifted the rear. Both cranes worked in perfect unison, with constant communication between the operators to maintain the correct angle and steady movement. The synchronized effort ensured the rotor was lifted smoothly, preventing any strain on the equipment or risk of damage to the generator components. This careful approach ensured a safe and efficient removal. After the rotor was carefully detached, it was transported to a designated temporary storage area. 2 cranes continued to coordinate the lift, moving the rotor slowly and steadily to avoid any sudden movements. Once in the storage location, the rotor was secured and protected to prevent any potential damage before repairs.